Okay, we're going to go one by one talking about all of the various orbitals. So s orbitals, okay? So psi 100, so I've already demonstrated how we constructed this wave function, and a little tiny mistake there, that should be z cubed, right? You can see my Mathematica file there next to me, okay? And so again, remember the 100, that's n is 1, L is 0, and L is 0, okay? So a few qualitative points of discussion. The closer an electron is to the nucleus, the lower is its potential energy. And one reason for that is because here we note that the high degree of curvature, if you recall from way back in chapter 7, a large curvature in our wave function corresponds to a large kinetic energy through second derivative analysis, okay? So that means up in this region, the closer the electron is to the nucleus, the higher is its kinetic energy. Okay, and so as it gets farther away, this region of low curvature indicates that its kinetic energy is becoming very low, but its potential energy is becoming very high. Okay, and our s orbital wave function is spread out, so it's smeared out, just like you can see with this exponential decay, right? And it's spherically symmetrical. All right, so this is just looking at the radial component. I know I've plotted the whole psi 100, but on this type of graph, it's only going to show us the radial component. But if we look at a three-dimensional representation, we can see that exponential decay given as this shaded area, right? So you can see here where this dark color, it's much darker at the origin, so that indicates higher probability at the origin. And as we move further away, we have decaying probability. Okay, and that's spherically symmetrical. So hopefully, what you're familiar with, if we look at the 2s orbital, and so let's just back up really quick and look at the radial graph. I've got that right here. Okay, so remember there was one node on the 2s orbital. And we can see that on this spherical plot right there. Okay? And so what ends up happening then is at the first region, we have this exponential decay. Okay? But then in the second region, so I'll kind of try to represent that with my red color, looking something like that. But in the second region, it's not so much of an exponential decay as it's some function that hits a maximum and then decays again. And if I'll go back to that radial profile and show you that, you can see that right here, okay, where there's this decaying region. And then even though this goes to negative values, oh no, my mouse battery is low. I hope it doesn't run out during this recording. So this region right here, if we were to plot that region as psi squared, that's going to give us that maximum that I drew right here, okay? So I like to kind of call these the onion layers. And hopefully, as you remember, when we go to 3s and 4s and 5s, we get more and more of these onion layers, okay? So let's keep talking about s orbitals. And now what I want to get into is their what's called the radial distribution, PR, okay? So we recall that when we take the square modulus, this gives me the probability of finding the particles somewhere. Okay? And so if you recall now, if I put this whole thing together, right, as it turns out, I'm not going to show this derivation, but for all spherically symmetrical wave functions, we can create this probability distribution by going 4 pi r squared times psi squared. So where does all that stuff come from? Well, I'll remind you, d tau, right, when we carry out this operation right here, okay, and then again, noting that psi 100 equals r of r 10, and then y of theta phi 00, right? Well, when we put all that together, okay, remember that the YLM, so I'm only going to draw that portion here on the integral, 0 to pi and then 0 to 2 pi of the YL ML, and then square modulus, right? Squared. And then remember that we have this sine theta, d theta, d phi. Okay? And then we also have that radial component, 1, 0 of r times r squared dr from 0 to infinity. So we recognize that all of this is normalized in the sense that it's all equal to 1. Okay? So what ends up happening here, we're going to define this function p of r dr as, and I'm going to drop the integral here, of just r of r squared dr. And then now all of this stuff is already normalized to 1. Okay? So the dr and the dr cancel, and we get that PR equals R times R squared. And this ends up being the case for all spherically symmetrical, or for all non-spherically symmetrical wave functions. And buried within the proof that I'm not going to go to in full detail, for all spherically symmetrical wave functions, it's an additional factor of 4 pi. Okay? And I should say that equals 4 pi R squared times r of r squared. Because in this sense, the spherically harmonic wave function is normalized to 1. And again, we have to include that additional 4 pi factor for spherically symmetrical wave functions. So what does this graph look like? Let's see here. So here I've got it plotted out, okay? And then remember that's z cubed, okay? And so I've also got that on my Mathematica file right here. And I've got that on a manipulate, so I can change the charge. Okay, so remember, z equals +1 for hydrogen. And so when we look at this radial distribution for the 1s orbital, so this is 1s, this is really cool. Check it out. The maximum, if we look at where that is, and you trace it down, it's right around 50 picometers. Okay? Can we get a more exact value of that? Well, we can. And so how would we do that? Well, if I want to find the maximum, I would say take d p of r dr and set it equal to 0 and solve for r that satisfies that equation. Well, I did that in my Mathematica right here, okay? So you can see I've got, I'm calling it most probable radius, and I'm solving. Here is the derivative of my psi 1, 0, 0, and then I've got 4 pi r squared psi squared, okay? So I'm doing the proper radial distribution function that I put together right here, okay? And I've set that equal to 0, and I'm solving for r. And I've also, on my code right here, that number 1 that I've highlighted, that z is equal to 1. And check it out. We get A for the Bohr radius. Very cool. So that peak is, in fact, 52.9 picometers. And the most probable radius for finding the 1s electron and hydrogen is the Bohr radius. Very cool stuff. Okay. So now what happens when we change the charge, the internuclear charge? What effect does that have? So we're still just looking at psi 1, 0, 0, so 1s. But suppose we change the charge to z plus 2. Okay. Check out what happens. Ooh, look, it moved closer to the nucleus. And if I go z plus 3, it moves even closer to the nucleus. And if I keep going with this, right, +4, +5, +6, okay, you can see that the function is getting more compressed because it has to be the same area. All we've done is change the z. So for the same area, it has to become more compressed and taller. But that changing that internuclear charge to higher values has the effect of sucking the electron in even closer, which is what we remember from our general chemistry days, okay? And what's also really cool on solving where that maximum is occurring, So here on my little Mathematica problem, I can just make the z equal to 2 right there. That's what I just did. And I'll evaluate it. And look, the most probable radius becomes a over 2. And if I go to 3, it becomes a over 3. And if I go to like 7, it becomes a over 7. Okay. So what's going on there is now if you look at all of these calculations, so this is what I just did, right? And so remember, this is still just a one electron system, okay? So all we're doing is just adding more protons into the nucleus, right? And so you can see the effect that has by changing the nuclear charge with only one electron. It really dramatically sucks the electron in closer to the nucleus. And that's represented by this picture right here, okay? Very cool stuff. And so even though on the, on the periodic table and in reality, we don't have like carbon 5 plus or boron 4 plus or whatever, but that effect still manifests into the multi-electron atoms. As we increase the charge in the nucleus, it has the effect of bringing the electron closer in, okay, which we can see in this simple model. Very cool stuff, okay?